The rifle lay disassembled on the steel workbench at the Manufacture d'Armes de Saint-Étienne. March 1973. Paul Tellie stood over the components, arranged in the precise order of reassembly. Receiver, bolt carrier, two-piece lever, trigger linkage rod, magazine well. Around him, the arsenal's machinery hummed through its second shift, lathes cutting barrel blanks, presses stamping receiver halves, quality inspectors checking tolerances with calipers. Tellie had been chief engineer here for 8 years. He'd overseen production of the MAS-49 rifle, the MAT-49 submachine gun, and modifications to existing systems. This project was different. The French Army had issued a requirement: create a rifle with a 19.3-inch barrel that measured less than 30 inches overall. Conventional design couldn't achieve it. The math didn't work. He picked up the receiver. In a traditional rifle, this component sat in front of the trigger. The barrel attached to its front end, the stock to its rear. The entire internal mechanism occupied the space between the operator's hands and shoulder. This layout had been standard since the 1840s, refined through a century of engineering iteration. Tellie had reversed it. The receiver now sat behind the trigger, tucked against the operator's shoulder. The trigger connected through a linkage rod, a simple metal bar that ran the length of what would normally be the stock. When the trigger was pulled, the rod transmitted that motion rearward, engaging the internal mechanism. This configuration had a name: bullpup. The British EM-2, the Soviet Korobov designs, and experimental American prototypes, all had attempted it. None had entered full production. The challenges were consistent: awkward ergonomics, complex trigger mechanisms, and ejection ports too close to the operator's face. But the spatial advantage was undeniable. Tellie measured the prototype. Total length, 757 millimeters. Barrel length, 488 millimeters. The ratio was unprecedented for a service rifle. This compact envelope would fit inside the AMX-10P infantry fighting vehicle, where personnel sat shoulder to shoulder in a space designed for submachine guns. The French Army needed this capability. NATO doctrine emphasized mechanized movements, personnel transported in armored vehicles, dismounting only when necessary. But existing rifles were too long. Personnel couldn't move efficiently inside vehicles while carrying them. They couldn't aim through vehicle ports. They couldn't transition quickly from transport to active engagement. Tellie reassembled the receiver group, sliding the bolt carrier into its rails. The delayed blowback lever clicked into position, a small, precisely machined component that would define the entire system's operation. He locked the mechanism housing into place and connected the linkage rod. The rifle took shape. In 3 weeks, it would undergo its first live tests at the arsenal's proving ground. In 5 years, it would enter production. In 7 years, French units would carry it through the streets of Beirut, across the deserts of Chad, and into the jungles of French Guiana. But on this March afternoon, it existed only as an assembly of machined parts, a geometric solution to a spatial problem. If stories like this help you see how engineering quietly shaped history, tell us in the comments what surprised you so far. And stay with us for the next chapter. Paul Tellie had received the specification document in October 1971. Direction Technique des Armements Terrestres, the Army's technical directorate, had been explicit. Maximum overall length, 750 millimeters. Minimum barrel length, 480 millimeters. Caliber, 5.56 45 millimeter NATO. Rate of engagement, 900, 1,000 rounds per minute. Weight, under 4 kilograms loaded. The barrel requirement was non-negotiable. Ballistic studies showed that 5.56 mm rounds needed at least 480 millimeters to achieve stable velocity. Shorter barrels created excessive flash, reduced accuracy, and failed to perform as designed upon impact. The system's effectiveness depended on that length. The overall length requirement was equally rigid. Interior dimensions of the AMX-10P measured 2.1 meters from front bench to rear ramp. 8 personnel sat in 2 rows, 4 per side. If each carried a 900mm rifle, the standard length of the FAMAS's predecessor, the FAMAS 49-56, they would be striking each other's equipment with every movement. Vehicle interior efficiency would drop by 30%. Tellie had calculated the math repeatedly. A traditional rifle layout required approximately 200 millimeters forward of the chamber for the barrel attachment and front sight, 150 millimeters behind the chamber for the bolt carrier travel, and 200 millimeters further back for the stock. Total, 550 millimeters of non-barrel length. Add a 480 millimeter barrel, and the minimum possible length was 1,030 millimeters. The specification demanded 750. The only solution was to eliminate empty space. In a bullpup configuration, the stock became the receiver. The space behind the chamber occupied the same volume as the space behind the operator's trigger hand. Bolt carrier travel occurred inside what would traditionally be dead space. This recovered approximately 200 millimeters, but bullpup designs carried inherent problems. The British EM2 had been shelved in 1951, partly because personnel found its balance unnatural. The trigger pull was described as long and creepy. The linkage rod introduced flex that degraded precision. Ejection port proximity meant spent cases exited centimeters from the operator's cheek. For left-handed individuals, this made the system nearly unusable. Tellie addressed each issue systematically. The trigger linkage required a rigid rod with minimal clearance in its guide channels. He specified a diameter of 4 millimeters with a straightness tolerance of 0, 5 millimeters per 100 millimeters. The rod would be hardened steel, surface ground after heat treatment. The trigger mechanism itself would be a 2-stage design, standard for the era, but with shorter engagement distances to compensate for linkage length. The ejection port problem was trickier. Most bullpups ejected straight out the side. The FAMAS would eject forward at a 30-degree angle, using a deflector built into the bolt carrier. This required precise timing. The case had to clear the ejection port before the bolt began its return stroke. At 1,000 rounds per minute, that timing window measured 0.06 seconds. The delayed blowback system became the solution to multiple problems simultaneously. By controlling the bolt's rearward travel, it regulated ejection timing, reduced felt recoil, and maintained a high rate of operation. The lever arm that created the delay was 60 millimeters long, pivoting on a hardened pin. When the bolt moved rearward, it contacted the lever at a mechanical disadvantage. The lever's geometry forced the bolt to travel 12 millimeters before the lever would pivot fully and release it. Tellie built the first functional prototype in January 1972. It functioned for 6 cycles before the trigger linkage rod bent. He replaced the rod with a thicker version. The second prototype functioned for 200 cycles before the delayed blowback lever cracked at its pivot point. He redesigned the lever with a larger pivot pin and heat-treated the entire component to Rockwell 58 hardness. The third prototype completed 2,000 cycles without failure. In April 1972, the direction technique authorized full development. The specification had been impossible. Tellie had made it possible by eliminating the assumption that a rifle's receiver had to sit in front of its trigger. The delayed blowback lever measured 60 millimeters from pivot point to contact surface. It was machined from a single piece of steel, heat-treated surface ground. In the assembled rifle, it sat at a 35-degree angle, positioned so the bolt carrier's rearward motion would strike it at a mechanical disadvantage. When a cartridge is engaged, the projectile accelerates down the barrel, while chamber pressure peaks at approximately 3,800 bar, 54,000 pounds per square inch. This pressure pushes in all directions, forward against the projectile, outward against the chamber walls, and rearward against the bolt face. In the FAMAS, that rearward force began pushing the bolt carrier backward the moment ignition occurred. but the bolt couldn't move freely. As it traveled rearward, a cam surface on the bolt carrier contacted the lever arm. The lever's geometry created resistance. The bolt had to push the lever through its arc of rotation, approximately 15 degrees, before the lever would clear and allow the bolt to continue. This delay lasted 0.003 seconds. During that interval, chamber pressure dropped from peak to approximately 800 bar. The projectile exited the barrel. Gas pressure bled off. By the time the lever cleared and the bolt carrier moved freely, pressure had fallen to safe levels for the extraction process. The lever's contact surface showed wear patterns after extended use. Tellie's team had photographed these patterns at 500-cycle intervals. The wear was consistent, predictable, contained to a 4 mm zone. This indicated proper load distribution. The lever wasn't failing, it was functioning as a precisely controlled wear surface. The two-piece design was critical. The lever itself was one component. The pin that held it was another. If the lever ever failed, cracked, bent or broke, the pin would remain intact. The bolt carrier would stop. The system would cease operating immediately rather than experiencing a catastrophic mechanical failure. This was engineered fail-safe behavior. Testing at the Bourges Proving Ground had verified the system under extreme conditions. Frozen units at 35 degrees C, units heated to 70 degrees C and immediately operated, units submerged in sand, mud, salt water. The lever system continued functioning. The delay timing remained consistent within 5 seconds across temperature ranges. This precision wasn't accidental, it was the result of material selection, heat treatment specification, and dimensional tolerances held to 0.02 millimeters. The rate of operation, 1,000 rounds per minute, was a direct consequence of the lever design. By controlling the bolt's motion through mechanical delay rather than gas operation, the system eliminated several time-consuming steps. No gas tube to fill, no piston to travel, no rotating bolt to unlock. The lever pivoted, the bolt moved, the cycle completed. Each cycle took 0.06 seconds. This speed created training requirements. A 25-round magazine emptied in 1.5 seconds on full automatic. Personnel had to learn control at a level not required with slower operating systems. The French Army developed specific drills: 2-round bursts, 3-round bursts, controlled automatic operation. The rifle's capability exceeded most tactical requirements, which meant restraint became a training priority. The ejection pattern was equally precise. Cases exited forward and right at a 30-degree angle, traveling approximately 2.5 meters before landing. This pattern resulted from the ejection port's angle and the case's rotational energy as it left the chamber. Tellie had calculated this trajectory to ensure cases would clear the rifle's body without striking the operator's face or the weapon's own structure. For left-handed operators, the solution was a modified bolt carrier with a reverse deflector. This required professional-level installation, not something a user could change in the field. The modified carrier redirected cases forward and left, maintaining the same 30-degree angle and 2.5-meter throw distance. The French Army eventually standardized on right-hand ejection, training left-handed individuals to operate right-handed instead. The delayed blowback lever, smaller than a human finger, controlled all of this. It regulated timing, controlled pressure, maintained rate of operation, and ensured safe function across environmental extremes. Every other component in the FAMAS existed to support what this lever made possible: full rifle capability in a compact envelope. Do you think this design choice was inevitable or a risky gamble at the time? Share your view in the comments and pass this story to someone who enjoys understanding how things really work. The first 500 rifle production run began in November 1976. Each rifle was pressure tested with 3 rounds at 30% overpressure. cartridges loaded to 4,140 bar instead of the standard 3,800. If a receiver was going to fail, it would fail during testing, not in a user's hands. 17 rifles showed micro cracks in the housing. They were scrapped. The remaining 483 went to the French Army's Evaluation Directorate. Field testing began at the Canjuas military camp in southeastern France. Platoon-sized units conducted live exercises, movement drills, magazine changes under time pressure, operating from vehicle ports, nighttime operations. After 2 weeks, the reports identified consistent issues. The trigger pull averaged 2 kilograms, significantly heavier than the specified 4.5 kilograms. The linkage rod was binding in its guide channels at certain temperatures. Tellie's team traced the problem to thermal expansion. At 40 degrees, the polymer guide channels expanded just enough to create friction against the rod. The solution was to reduce the rod diameter by 0.15 millimeters and increase guide channel clearance by the same amount. This created a looser fit, but one that remained functional across temperature ranges. Magazine reliability was inconsistent. The FAMAS used a 25-round straight magazine, narrower than the curved magazines common to other 5.56mm systems. This straight design was necessary for the bullpup configuration. Curved magazines created awkward insertion angles, but the straight design increased spring pressure requirements. Some magazines failed to feed the last 3 rounds reliably. The magazine spring design was revised. Original springs were wound from 1mm wire at 12 coils per 25mm. The revision used 1.2mm wire at 10 coils per 25mm. Fewer coils, thicker wire, higher compression strength. Magazine reliability improved to 99.7%, acceptable for service standards. The carrying handle, which doubled as the sight base, showed a tendency to loosen after repeated operation. This was a resonance problem. The rifle's vibration frequency during automatic operation matched the natural frequency of the handle attachment screws. Over time, vibration loosened the threads. The solution was to add spring washers under each screw head and apply thread-locking compound during assembly. Accuracy testing revealed an unexpected characteristic. From a bench rest at 100 meters, the FAMAS grouped shots into a 4-centimeter circle, adequate for service use, but not exceptional. However, when operated from standing or kneeling positions, groupings tightened to 3.2 centimeters. This counterintuitive result occurred because the rifle's rearward weight distribution reduced the effect of user-induced movement. The weapon's balance compensated for human instability. The bipod, integrated into the handguard, created interference with certain equipment. Personnel wearing standard French Army load-bearing gear found that the bipod's folded legs caught on pouch flaps during rapid reloading. This wasn't a rifle defect, it was an equipment compatibility issue. The Army revised its equipment specifications to accommodate the FAMAS dimensions. Environmental testing at the Bourges proving ground subjected rifles to accelerated wear cycles. One rifle was operated continuously until failure, 22,000 cycles before the barrel throat eroded beyond acceptable accuracy standards. Another was frozen, thawed, and operated repeatedly for 3 weeks. A third was exposed to salt fog for 72 hours, then operated without cleaning. All continued functioning within specification. The delayed blowback lever showed consistent wear patterns across all test rifles. After 10,000 cycles, the lever's contact surface had worn approximately 0.8 millimeters. At this wear rate, the lever would require replacement after 50,000 cycles, well within the rifle's expected service life. The wear was predictable, measurable, and non-critical. By March 1977, the Evaluation Directorate had collected data from 156,000 cycles across 483 test rifles. Their conclusion: the FAMAS met or exceeded all specified requirements. The bullpup configuration, initially viewed with skepticism by traditional officers, had proven functionally sound. The delayed blowback system was reliable, the compact dimensions were tactically advantageous. In August 1977, the French Army issued its adoption order. The FAMAS would replace the FAMAS 4956 as the standard service rifle. Production would scale to 30,000 units per year. Paul Tellie's geometry had become French military doctrine. The bullpup configuration was not an aesthetic choice. It was a forced solution to an impossible requirement. This distinction mattered because it explained every compromise built into the FAMAS. Traditional rifle layouts evolved over 150 years to optimize human ergonomics. The trigger sat near the rifle's center of gravity. The stock extended behind the action, distributing recoil across the operator's shoulder. The sights mounted above the barrel axis, creating an intuitive sight picture. This layout wasn't arbitrary. It represented cumulative refinement through millions of cycles and thousands of design iterations. The bullpup abandoned this refinement. By moving the action rearward, it shifted the center of gravity back by approximately 15 centimeters. The trigger no longer connected directly to the internal sear. It connected through a linkage rod, introducing mechanical complexity and potential failure points. The ejection port moved closer to the operator's face. The charging handle became ambidextrous by necessity, as there was no longer a clear offside of the weapon. These weren't flaws. They were the inevitable consequences of prioritizing length reduction over ergonomic optimization. Tellie understood this from the beginning. The specification demanded a 750mm rifle. Physics and geometry provided only one path to achieve it. That path required accepting specific trade-offs. The delayed blowback lever existed because the bullpup configuration made gas operation impractical. In a gas-operated rifle, a tube runs from the barrel to the bolt carrier, channeling propellant gas to drive the action. This tube occupies space. In a traditional layout, that space sits above the barrel, contained within the handguard. In a bullpup, that space doesn't exist. The barrel extends nearly to the rear of the receiver. Tellie could have used a short-stroke piston system, where gas acts on a piston that strikes the bolt carrier, but this added weight and complexity. The delayed blowback solution was mechanically simpler. Let the bolt move freely, but delay its motion just long enough for pressure to drop. The lever was the minimum necessary mechanism to achieve this delay. The 1,000 rounds per minute rate of operation wasn't a design goal. It was a side effect. By eliminating the gas system's travel time, the delayed blowback system completed its cycle faster than comparable rifles. The FNFAL operated at 650 rounds per minute. The M16A1 operated at 800. The FAMAS operated at 1,000, not because personnel needed that speed, but because the mechanism operated that efficiently. This high rate created the magazine capacity problem. A 30-round magazine would be proportionally longer than a 25-round magazine, making the rifle's overall length slightly longer. The specification demanded 750 millimeters. A 30-round magazine would add 18 millimeters. So the FAMAS used 25-round magazines, and personnel learned to manage their logistics accordingly. The right-side ejection limitation was similarly geometric. Bullpup rifles eject near the operator's face. Ambidextrous ejection requires either a forward ejecting system, complex and heavy, or a field-changeable bolt carrier. The FAMAS used a field-changeable system initially, then standardized on right-side ejection. When training left-handed individuals to operate right-handed proved simpler than maintaining dual inventory. Every characteristic of the FAMAS traced back to the length requirement. The carrying handle existed because a rear-mounted sight wasn't feasible. The bipod integrated into the handguard because there was no other place to mount it. The trigger guard was oversized because winter gloves were mandatory issue and there was no room for error in manual operations. Nothing was stylistic. Everything was necessary. This was what made the FAMAS significant. It proved that a bullpup rifle could function reliably in professional service. Not perfectly, not ideally, but adequately. The British SA-80, the Austrian AUG, the Israeli Teva, all benefited from the lessons the FAMAS demonstrated. Bullpup configurations were viable. The trade-offs were acceptable. Tellie hadn't invented the bullpup. He'd proven it worked. The FAMAS entered full service with the French Army in 1980. Over the next 3 decades, approximately 400,000 rifles were manufactured. They served in Lebanon, Chad, French Guiana, the Balkans and Afghanistan. French units carried them. Foreign Legion personnel qualified with them. Maritime units used them in sea operations. The rifle's compact length proved its primary advantage. In urban operations, where personnel moved through doorways, climbed stairs, and maneuvered in close quarters, the 757mm length was measurably superior to 900mm conventional rifles. Reports from the 1982 Lebanon deployment specifically noted this advantage. Personnel could transition from vehicle to building interior without the weapon becoming unwieldy. But the trade-offs persisted. The trigger pull, even after refinement, was described as adequate but not excellent. The right-side ejection remained a limitation. Approximately 12% of French personnel were left-handed and had to adapt. The 25-round magazine capacity was sufficient, but not generous. The high rate of operation required disciplined control that not all users mastered equally. Other nations observed these characteristics. Austria developed the Steyr AUG with a modular design that addressed some of the FAMAS's limitations. Israel created the Teva with a longer sight radius and improved ergonomics. Britain adopted the SA-80, though early versions had significant reliability problems. Each design incorporated lessons from the FAMAS's service record, proof that the bullpup concept was viable and evidence of where it could be improved. The delayed blowback system, the FAMAS's defining mechanism, did not propagate to other designs. Most subsequent bullpups used gas operation or short-stroke pistons. This wasn't because the delayed blowback system was flawed. It functioned reliably for 3 decades. Rather, it was because other designers prioritized different characteristics. Gas systems allowed adjustable rates of operation. Piston systems isolated the bolt carrier from propellant residue. The delayed blowback system's simplicity was an advantage for the FAMAS's specific requirements, but not universally optimal. By 2010, the FAMAS was showing its age. Barrel life averaged 12,000 cycles, acceptable for certain service structures, but limiting for professional forces conducting high-volume training. The rifle couldn't reliably use NATO standard ammunition from other nations. The chamber was optimized for French-manufactured cartridges, which had slightly different dimensions. Parts availability declined as production ended, and the Saint-Étienne arsenal shifted to other projects. In 2016, the French Army announced the FAMAS would be replaced by the Heckler & Koch HK416, a conventional layout gas-operated rifle. The official reasoning cited parts availability, ammunition compatibility, and accessories standardization. The HK416 measured 880 mm with its stock extended 130 mm longer than the FAMAS. Vehicle interior dimensions were no longer the constraining factor they had been in 1971. Tactical doctrine had evolved. The FAMAS remained in service through 2020, then was gradually withdrawn. After 40 years, its operational service ended, but its influence persisted. It had demonstrated that a bullpup rifle could serve as a primary service weapon for a major military. It had proven that compact length could outweigh ergonomic compromises in specific tactical contexts. It had shown that delayed blowback was a viable operating system for military use. Paul Tellie retired from the Saint-Étienne arsenal in 1989. By that time, the FAMAS had been in production for 13 years and had been carried by hundreds of thousands of French personnel. The rifle he designed wasn't revolutionary. It didn't introduce new materials, new propellants, or new sighting systems. It was a geometric solution to a spatial problem, executed with precision and successfully deployed at scale. That was its legacy. Proof that engineering constraints, properly understood, could be converted into functional designs. The FAMAS worked because Tellie had accepted what the bullpup configuration demanded and designed every other component to accommodate those demands. The rifle was the constraint made physical. If you enjoy calm, true stories about how engineering shaped the world, subscribe to the channel, leave a like, and tell us from which country you're watching.